talked about. Some of you actually read more about those classification techniques like random forest and other classifiers, which is very good. In the first class a few weeks ago, we mentioned that there are mainly two types of machine learning problems. The first one is classification, in which the response, the label, is discrete. Right? In the case of binary classification, we can just assume the label are positive one and a negative one. And in the case of a multi-category or multi-class classification, usually you can use so-called one-hot encoding. Right? If you have k classifiers, you have each label is a k-dimension vector, with only one being 1 and all the others are 0. Right? Or in the simplest case, it's just 1, 2, 3, 4, 5. It's just discrete values. But then there's another, the second important problem in machine learning is so-called regression. Right? In the case of regression, the only difference is now the label or the response is a real value instead of a discrete value. Right? Typical examples include, for example, predicting the housing price given the historical data as a training example. Right? You want to predict how much a house might be worth. Right? Also, for example, to predict the stock shares price, which is a time series regression problem. Right? The input is a time series, and the output is a price of a particular stock. Right? So that's regression. Okay? So really, the only difference between classification and the regression is the response. The label is different. And actually, in some cases, you can convert a regression problem into a classification and vice versa. In some cases, it's possible. And same as classification, we have quite a few different regression techniques. And in today's lecture, we only cover two very simple ones. The first one is linear regression, which might be the simplest regression technique. And in real world application, unless you have very powerful representation of the input data, linear regression may not work that well. So then the second technique we will talk about is support vector regression. And as the name indicates, you can imagine that it's just an extension of the support vector classifier that we have learned 2 weeks ago. Okay, so let's start from the linear regression. Here I just give you some. Well, that's what I talked about, right? So the classification and the regression. Actually, the third one is clustering, which we talked about a few weeks ago. K-means clustering. That's unsupervised learning, right? Gaussian mixed model, expectation maximization algorithm for estimating the Gaussian mixed model's parameters. That's unsupervised learning. But then the other two is classification and regression. And as you can see, classification basically give a bunch of data. You want to find a separation hyperplane, which is a classification boundary to separate the different sets of the data points. But for regression, actually, given a set of data points, you want to find a straight line if it's a linear regression model, or a hyperplane, a curve to fit the given data points. Okay? So in some sense, it's like you want to find a parametric model to represent the data points. Right? Find a model that can explain the output given the input. All right? That's the high-level idea of regression. Well, we actually talked about this, this pipeline a little bit a few weeks ago. So given the raw data, you do the pre-processing first, and you extract the features, and then you fit the regression model. So this is pretty much, the overall pipeline is pretty much the same as you train a classifier, right? The first two steps are exactly the same, and only the learning part is different. Here I just show a very simple examples, right? So the first step, you might find some outlier, and you just discard the outliers. And you might also want to do a feature selection, right? In this case, the height and gender seem to be irrelevant. Right? And after you select the features, you fit the regression model. Okay, so again, actually, it's the same as in the case of classification, where for the linear regression, we have a linear function, which is W transpose X plus B plus epsilon. Or this epsilon is not the parameter to learn. It's just the noise, right? So the model is W transpose times X plus B, right? This is exactly the same as the linear classifier. And W and B are the parameters that we have to estimate. Okay, and the data points, except that X is a real value. Again, it's the same as binary classification, right? So in the case of linear regression, we just minimize this reconstruction error. Okay? So y is the ground truth, right? And this is a output W transpose W times W inner product of W and Xi, which is the same as W transpose times Xi plus B. That's the regression model's output, right? The response. And you minimize the difference, the squared difference for each data point, right? So this is a linear regression model. And the objective function basically is a so-called reconstruction error, and we minimize this reconstruction error. The optimum, the minimum for this optimization problem can be found by solving this equation, right? It has a closed form solution. It's very easy to get this solution. All you need to do is just partial, if we call this f, partial w, set it to be 0. Then you will arrive at something like this. Okay? Yes?
When do you get like a factor of b? Take a partial?
When you take the partial f, partial w, the b just doesn't have any impact, right? It's just 0. Right? But if you wanted to find the b, then you just partial f, partial b. You need to set that to be 0 as well. Okay? W and b are two sets of variables. At the optimum, the function with respect to each variable, the differential should be 0. The gradient should be 0. Okay? So this is just the solution of W. This is just a solution of W, right? And actually, B, thinking that way, if you append X, each feature vector by a constant 1, then you can absorb B into W. Right? So in that sense, the offset is not that important. But in any case, to find B is easy. And in MATLAB, you can just do using the backslash operator, and it just calculates using this least square minimization, basically. So this is the simplest linear regression. And this actually, when I mentioned reconstruction error, does that remind you something? Well, previously we learned about principal component analysis, PCA, right? We talked about, PCA actually, the principal component minimize the reconstruction error, right? Anyway, if you forgot, just check go back and check the PCA slides. Right? So it has some connections. Okay, so that's the linear regression, right? But then we said in machine learning, to avoid overfitting is really important. So that's why for almost all the machine learning optimization problem, we have two terms. One is the training error. We try to minimize the training error. In this case, the reconstruction error is a training error. But then we have the second term, which is the regularization. Right? We apply a regularization term just to avoid overfitting. So if you don't apply any regularization term, in the case of you don't have enough training data, then it's not a good idea. So we can apply a regularization term to this linear regression reconstruction error, the object function, right? So we can, for example, we just apply this A1 norm, okay? This is the A1 norm of the W, right? We don't want the magnitude of the parameter W to be too large, okay? So we can just use the A1 norm, and this has a particular name called lasso, right? In this case, we are not able, we don't have a closed form solution anymore. So we need some more sophisticated technique to solve this problem, because now we have this, which is the sum of the absolute value of each component in W, right? That's the A1 norm. So the optimization becomes more complex, okay? Actually, we can just use this so-called linear programming technique to solve this problem, if you like. Right? Of course, there are some other techniques to solve this. Remember, for the first assignment, you are asked to implement, to formulate this quadratic programming problem, right? And this problem, this lasso optimizing problem, can be reformulated into a so-called linear programming problem. In the case of quadratic programming problem, the objective function is quadratic, subject to a set of linear constraints. In the case of linear programming, actually, it's simpler, because in linear programming, the objective function is linear. It's not quadratic, it's linear, and subject to a set of linear constraints, which is the same as in quadratic programming. Okay, so just remember, if you want to solve this one, you can just call any off-the-shelf linear programming solvers. Okay, but again, just recall that in support vector machines, we also have this regularization term on W, right? But it's not L1 norm, it's L2 norm. So we can also apply L2 norm. Here, this absolute value operator is redundant, right? We don't need to have this because it's always positive, non-negative. So in the case that we apply this L2 norm as a regularization, then it has a name. It's called a ridge regression. Right? Anyway, it's just a different regularization term. So, any questions so far? I believe this is very simple, right? It's just a linear model, and we just apply. We can apply two different norms for regularizing the objective function to avoid overfitting. Okay, so this is linear regression. As I said, in practice, usually it's not very useful because your data, your real-world data, typically do not follow a linear model, right? We need nonlinear regression, which I will talk about a little bit later. Okay, so this is linear regression. So now, the second technique we want to talk about is support vector regression. And this is very similar to support vector classification. Okay, so when we studied the support vector classification, support vector machine for classification, we started from the so-called hard margin case. And let's look at the hard margin case for regression, right? So let's check this plot, okay? The only difference between this support vector regression and the linear regression is now we just define a margin, okay? So the margin is epsilon here, right? The idea is if the data points, for the data points that are in the margin, in this region, this data point will not incur any loss, okay? It will not incur any penalty. So we just assume this data, in terms of the error is 0. Only for those data points that are outside of this margin, they will incur a penalty, okay, a loss. Right? Again, this is the same as in the case of classification, right? So, and sometimes this is also called epsilon insensitive loss, which is, if the error is less than epsilon, there's no loss, okay? So that means, we do not care about the errors as long as the errors are less than epsilon. So that's the whole idea of support vector regression, right? It's different from the case of linear regression because for linear regression, only the data points that are exactly on the line will not incur loss, right? All the other data points that are offline, that are not on the line, will incur loss. But here, you basically generalize, you extend the, this straight line into a margin, right? If the points are in the margin, they will not incur loss. And mathematically, we can just use two, constraints to formulate this, right? So we want for the data points that are above this straight line, this linear function, which is this, right?
What is W1?
Sorry.
What is W1?
Oh, here it should be the same. Sorry, it should be only one W. All right. I think this is a typo. We only have W, not W1. We only have one set of parameter W. Okay, this is a typo. This is not W1. So for the data points that are above the line, so we want this value less than epsilon. Okay? And for the data points that below this line, this value should be less than W. It's just these two sets of constraints represent the data points. One set of data points are above the line, and the other one is below the line. Okay, and we want all the in the hard margin case, we want all the training data, are between to be between the margin. So we want all of the data points satisfy these two constraints, right? And in this case, the objective function is only the regularization term, the L2 norm of the parameter W. Right? You can compare this with support vector classification. Right? It's very similar. Okay, this is hard margin, and again, same as in the case of hard margin support vector classification, you may not be able to find a solution to this problem if not all the training data are in the margin, right? In this case, let's say we do have one data point which is outside of this margin, then this problem becomes infeasible, right? You will not be able to find a solution. Then we need this soft margin, okay? We introduce a slack variable. Again, this is almost the same as the support vector classification. All right, so we can introduce a slack variable, Kc, right? Kc measures the distance from the data point to the margin. Okay. So only the data points that are outside of the epsilon region contribute to the cost. Will incur loss. Okay, and this is well, for the time being, let's assume we are learning a linear model. So same as in the case of linear regression, we have this linear function, right? And you can plot the loss function for this so-called epsilon insensitive regression loss. It's something like this, okay? It's something like this. So if you compare this with the classification is one-sided. Here it's symmetric. It's symmetric. But for the classification loss, it's asymmetric. It's something like this, right? So-called the hinge loss is something like this. All right. Mathematically, we can formulate this soft margin support vector regression, something like this, right? Almost the same as in the case of the classification. right? We introduce two slack variables, or two sets of slack variables. Actually, we just introduce each, two slack variables for each data point, okay? And we construct this slack variable to be non-negative. Again, this is the same as in the case of classification. But something different here is this constraint, this non-negative constraint, Xi star I must be non-negative. This constraint is redundant. This constraint is redundant. You can remove them without changing the solution of this problem. Why is that? It's not very difficult to see, right? Let's assume if the because it must be non-negative. If it's negative, we can safely set it to be 0. Is that right? No, actually, in this case, because the objective function here, I just write the sum of Xi itself. But in the case, if we use the L2 norm of the Xi to calculate the training error, then this Xi, this non-negative constraint becomes redundant, okay? But in the case, if we just calculate the sum of Xi itself, we do need this constraint. We do need this non-negative constraint, all right? This is the same as in the case of support vector classification. But there's another formulation. I think in the note we have slightly different. Okay, in the note we have a slightly different formulation. Here we just use the L2 norm. All right, use the L2 norm to measure the training error. Then in this case, the non-negative constraint for Xi can be removed without changing the solution. But in the case of, we just use, in this case is L1 norm to compute the training error, then we do need this non-negative constraint. So we can either use L1 norm or L2 norm, okay? It's the same as for the regularization. We can also use L1 norm. Yes?
Would you ever have two non-zero slack variables?
Non-zero slack variables.
You would only ever be one of them that's non-zero, right?
Yes. Only the other one will be 0.
So always be one or the other?
Yes.
Zero.
It's this is called a complementary constraint. So it's guaranteed, because the Xi times here Xi star equals 0. All right, so this is a linear case, right? This is a linear case. We can solve this problem using quadratic programming, as you did for the first assignment, right? You can solve this, because here the objective function is quadratic and all the constraints are linear, okay? Then we can solve this problem. How about nonlinear case? Right? This is, so far we only talked about a linear case. We are learning a linear function fx equals W transpose times x plus b. Right? Again, it's same as in the case of support vector classification. We can apply this so-called kernel trick to extend this into kernelized support vector machine or support vector regressions. Right? Here I just show you an example. But how we do that? The overall idea, again, it's the same. Actually, it's the same as in the case of support vector classification. We say that when we studied the support vector classification, we say that, given a bunch of data in the original space, you may not be able to find a linear classifier which separates the data points. So we lift the original data into a high dimensional space. Right? And in that high dimensional space, it's much easier to find a linear classifier, a linear function which can separate those data points. The high-level explanation is when you lift the original data from a low dimension space to a high dimension space, the density of those points become much sparse, right? Because in a high dimensional space, the data points tend to be very sparse. And because they are sparse, now it becomes much easier to find a linear function which can separate them. And here it's the same. So in the case that we are not able to find a linear function which can fit the data points very well in the original space, we'll lift them into a higher dimensional space. Okay, and in the higher dimensional space, it's more likely for us to find a linear function which can fit those data points much better. So we just need to map the original data into a higher dimensional space, right? Here I just show you an example. Right? We will actually take the square root and the square to be the new dimension, okay? And then in the new dimension, we fit the data. And in the same as in the case of support vector classification, we don't need to explicitly know the mapping function, right? The idea is instead of solve the original problem, we can solve the Joule problem, okay? When we solve the Joule problem, we just apply this kernel trick. We just calculate this so-called kernel function, right? So we only need to know the kernel function, the nonlinear kernel function, instead of the mapping function, okay? So given such a primal problem, okay, we can just derive its Joule problem. We can get something like this. All right, and in the Joule problem, you can see that the x, the input feature, only appear in the form of an inner product. Okay, so this is the inner product xi xj, the pairwise inner product. And we can just replace this inner product with a kernel function, with a nonlinear kernel function. And in most of the cases, we can just use this so-called Gaussian kernel. Sometimes it's also called RBF kernel. I'm not going to derive the Joule problem from the primal here, but it follows the same procedure as you did in the case of support vector classification, right? Exactly the same. You can just write the Lagrangian function and then partial the Lagrangian with respect to W and B and C to set them to be 0. And you just eliminate all the primal variables from the Lagrangian function, and then you only keep the dual variables, and you get the dual problem. I uploaded this note to the course website. You should check it. Here, in this note, all right. So this should be underneath or minimized. Okay. This does not read minus WC hat. This should be underneath. Okay. These are the variables. So this is the object function. But do remember here, the training error is a squared version. All right. It's not the linear version as we do here. So it's slightly different. And that's why the dual problem will be slightly different too. Okay? This is just two different formulation of support vector regression. And in most of the cases, they should work almost the same. Unless in the case that the data are extremely noisy, and then this formulation might work better because you are actually using the L1 norm to calculate the training error. And L1 norm typically is more robust than the L2 norm. But in general, they should work almost the same. All right, so again, this is the same as in the case of classification, right? So one of the things you need to do after this class is try to derive this dual problem from this primal, okay? Try to practice this. I can tell you this might be in the final exam. All right, so that's what I said. So after we have the dual problem, now it's become very straightforward to apply this so-called kernel trick, right? We just replace this linear inner product with a nonlinear kernel function, okay? This way, we don't need to know the mapping function phi, right? We only need to know the inner product of this mapping function, all right? So the two popular kernels we can try, one is so-called polynomial kernel. Remember here D is a hyperparameter. You have to choose a D before you train the algorithm. So in most of the cases, you just set D to be 2, right? And if you use this so-called RBF kernel, or the same as Gaussian kernel, this sigma is the kernel, the width of the kernel, of the Gaussian kernel. The sigma is a hyperparameter. You have to preset it before you train the algorithm. And for hyperparameter, one way to properly set the value is using cross-validation. Right? There's no principled way to find the optimal hyperparameter. Just remember, when you train a support vector machine for either classification or regression, in the nonlinear case, in the kernel case, most of the cases you can just use the RBF kernel or the Gaussian kernel. Why is that? We don't know. Okay, just empirically, RBF kernel works very well, right? And actually, there's no principled way to know which type of kernel works better than the other one. There's no such analysis at all, right? It's heuristic. That's why, in most of the cases, people just apply RBF kernel. So in the kernel in the nonlinear kernel case, I already talked about this. We just replace this inner product with a kernel function. That's all you need to do. So it's very simple. All right? So as long as you can calculate the kernel function, then you can solve this dual problem. It has, before the deep learning, before so popular like 5-6 years ago, support vector regression is one of the most popular methods for regression, right? And it actually, indeed, for some of the real applications, it works very well. For example, we can apply it to OCR, right? And stock price prediction, we can also, it's also a typical regression problem. We have a demo here. You can check the demo after the class. It's a JavaScript demo. You can add the training data. It's a 2D demo and see what the fitted function looks like in 2D. Okay. I might just skip some of the last few slides. It's talk about you can just use this toolbox called Weka, but it's Java. The programming language is Java, so I don't really recommend you guys to use Java, right? You can if you want to see how support vector regression works, you can just call scikit-learns API. Actually, I put a link to the scikit-learns support vector regression document on the course forum. You should have a look. And in terms of how do you evaluation the trained model, you can calculate the root mean square error or the mean absolute error, right? Again, the first one is just the L2 norm, and the second one is the L1 norm. Just skip the Weka. A few off-the-shelf tools you can use, right? Some C++ and there's another Python toolbox. And in OpenCV, there's also implementation for support vector machines. All right, we still have time. Let's check. Let's just briefly check this note. Okay, so do have a look. Do have a look at this note, and try to follow the mathematics here, right? This is a primal, and as I said, this primal is slightly different from the formulation in the slides. Okay. Then the procedure to derive the dual problem will be slightly different. All right. So I can tell you that for the final examination, I'm not going to ask you to derive this dual problem, but I may ask you to derive the dual problem from a slightly different formulation of this primal problem. Okay, so try to practice to derive the dual from any given primal problem. So the first thing you do is to formulate this Lagrangian, right? So the Lagrangian is very, very simple. You just copy the objective function here, and then for each constraint, you multiply a Lagrangian multiplier, right? You multiply alpha, okay, for each constraint, right? So for this constraint, you multiply alpha and sum them up, okay? And for this set, again, same, you multiply alpha hat here, and you sum them up. And because this is the inequality, right? Again, it's same as in the case of classification, because this is the inequality. This alpha and alpha hat must be non-negative, right? You do have the constraint. They must be non-negative. And in this case, this non-negative constraints are redundant, so you don't have it here, right? Why is that? Because let's say if it's negative, if alpha is negative, right? If it's negative, then it must, we can set it to be 0, such that the object function will become smaller, right? Because this is squared version of Xi. If it's non-negative, let's say if it's -1, then this will become 1. But if we set it to be 0, the constraint still hold, right? The set of constraints will still hold, but the object function, right, becomes smaller. So it's not possible for Xi to be a non-negative value, right? If it's non-negative, then it will become 0. That's why the non-negative constraint will be redundant. And the same for Xi, right? Okay, then after you write the Lagrangian, the remaining part is just the same. You just set the Lagrangian with respect the partial of the function with respect to the set of variables to be 0, and then you get something like this. And these equations are called KKT conditions in optimization. And you use this. You just put these equations back into the Lagrangian function, and you eliminate all the primal variables, and you keep the due variables. Then you get something like this. Okay, so this is a due problem. Just remember, this is different from the due problem in the slides, because of the way to calculate the training error is different. Okay, then we also have this so-called complementary slackness conditions. So this becomes 0. And if we introduce a new variable, you don't have to, right? But in this case, if you introduce some new variables, you can rewrite the due problem just to make it look similar to the case of classification. Okay, so this is the one we use in our slides. Okay, so you can, the way to calculate the training error can be linear instead of quadratic. In the case of linear, it's in a sense it's A1O, and we get something like this. All right, so the homework for you guys is to derive this primal, to derive the due problem from this primal. Okay, it's important. All right, any questions for the support vector regression? It's important because still, even today, if you have a very powerful feature, you can still apply support vector regression to get good results, given a real-world application problem. But of course, there are some other methods that you can apply to regression problems, like random forest, for example. And actually, even for the boosting methods, there are also regression versions. Any questions? All right. So then that's all for today. Next week, we are going to talk about deep learning. So next week and the week after, we are going, not the week after. I guess the week after is holiday. So next week and the lecture, after next week, we are going to talk about deep learning. As I said, deep learning is, if your problem has a lot of training data, then it looks like deep learning will outperform most of the traditional machine learning methods. So deep learning is very important. For next week, we will have a guest lecture, Dr. Wu, to talk about deep learning, because I will be away next week. All right, that's all for today.